here we go. In this video we're gonna learn about Dijkstra algorithm. So what is a Dijkstra algorithm? It is used to find the shortest path starting from any given source vertex. So let's suppose you are standing at a particular source and you want to reach each and every city, but you want to reach with a minimum distance. So that's when the Dijkstra algorithm comes in picture. So let's first look at the example, look at the problem. We have Dijkstra algorithm. You have given a weighted, undirected, connected graph where you have given urgency list, and you have to first find the shortest distance to reach all the vertices. So from the starting vertex, and we need to return in a list format denoting the shortest distance between each node and a source node. So the graph does not contain any negative edge. We're going to talk about this. So here we have to return in a list format, and you have given list inside a pair. So what is a pair? First first element of the pair is the neighbor node, and the second argument is neighbor weight. So we have this format. So it is connected to 1 and 1 with weight 9. So 0 is connected to 1 with weight 9. Then this 1 is connected to 0 with weight 9. So this is a undirected graph. So we need to reach to each and every vertex starting from 0. So to reach 0 itself, we does not need to take any path. So we have 0. To reach 1, we need to cover 9 distance. In this case we have this adjacency list. We have to start from 2. So starting from 2, if you want to reach 0, if you want to reach 0, so the shortest path is 4. So we have 4. Shortest path to reach 1 is 3. Shortest path to reach 2 itself is 0. So that's about it. So now let's try to understand Dijkstra algorithm. So we have this graph. So I have taken the graph. Before that, be sure to check out the Prim's algorithm first. So after that, only come over to this video if you have a clear understanding about the Prim's algorithm. So we're gonna uh, use the same steps. We will follow same steps, and I even taken the same graph from the Prim's algorithm video. So the video is given in the I button, so be sure to check out that video. Then let's talk about this algorithm. So we have to start from any given starting vertex. So let me take any random vertex. Let's suppose we want to start from 3. So in Prim's algorithm, what we did? First we inserted the source. In the Prim's we inserted 0 with 0, but in this case we have to start from a given vertex. So in this case we will just insert 3 and 0, 3 and 0. Then we will just pop out, and we have to build a array or a list. Starting from 3, we have to reach 1, 2, 3, 4, 3 and 4. So we only have 5 vertices. So we have this graph, this list. This is our answer list, and initially every element is maximum, and we want to find minimum. Then we also need visited array. What are the visited nodes? Initially every element is false. Then if we pop out this element, we can reach 3. If it is unvisited, yes, it is unvisited, then we will reach 3 with weight 0. So we just need to mark it with weight. So I marked it with weight. So we have a priority queue, and let me also build the tree just for visualization purpose. So 3. Then we have marked this 3. We want to traverse its neighbors. Is this neighbor visited? No. So we will add it 1 with 5. Then if we want to reach 2, so 2 is unvisited, 2 with 8. So we only have these 2. So then we will pop out this. Then we will pop out uh, smallest edge. Smallest edge. So then we got 1 and 5. We can reach 1 with weight 5. So is 1 already visited? No, it is not already visited. So we will just mark it with value 5. So this will look like this. Then we have marked it. Then what we'll do? Starting from this is visited, we will not consider this. This is unvisited. So we can insert 0 with weight 1, but this is wrong. We will not insert this. Why? Because we want to start from 3. We want to reach 0 starting from third vertex itself. So if we want to reach this node, the value will be 6 itself, not 1, not 0 1. The value will be 0 and 6. How do we get it value? So to reach this node, starting from 3 to reach this node, what's the distance we have to cover? It is given in our answer. It is given in our answer. So to reach third node, to reach this node, node number 1, to reach this we have to traverse 5. Then to reach it further, from the neighbor node to reach it further, we have to consider this and neighbor distance. We need to consider current distance plus neighbor distance. Then only we will add it. So what will add? I will add 0 with 6 because 5 uh, 5 distance we have to travel, then 0 distance we have to travel starting from this. So 5 we have to take. To reach 0, the weight will be 6. To reach 4, the weight will be 14. To reach 1, weight will be 14. Then to reach this, so the value will be 2 and 8. So we just need to add 2 and 8. What is the smallest value? Smallest value is this 0 and 6. So we will reach 0 with value 6. So is 0 already marked? No, 0 is not already marked. So we will just consider it true, and the value will be true and value is 8. So it will look like this. Oh, sorry, 0. 0 and 6. The value here is 6, not 8. Then to reach further nodes, it is already visited. Visited air will tell us it is already visited. So we are not interested in this. Side by side, let me also show you the code. Code is here. So what we have done, we have just pop out our value and we have just consider it. If the weight, added weight, is greater than already present weight, we will not consider it, else we will consider the weight. Then we are traversing the neighbors. So that's the step we are taking just now. First value is the neighbor node and the second value is neighbor distance. So let me dry run this. So neighbor distance, it is not visited. So I think I have not taken the visited here. So then what we will do here, we can reach the node 2 with weight. How many weight? To reach this node, we have to take 6. To reach it further, means to reach 2, we have to take uh, first neighbor second, means this value, then current weight to visit this particular node is 6. So to reach it further, we have to take 8. So is the value smaller? Is the neighbor distance smaller? Yes. So we can consider this. So now let's consider this. We can reach 2 with weight 8. This we can reach this node also. So 4. So we can reach 4 with how many weight? With weight 13. Then we will just pop out a value. So the value pop out is either be 2 8, 2 8 or 2 8. So we have 3 times 2 8. Anyways, so 2 8 will come out. Okay, so one way is this, second way is this, then third way is this. So that's why we have 3 times 2 8. So now 2 8 will pop out, and we have to just connect 2 with this 3, and the value present here is 8. To reach 2 we have to store 8, and it is visited. So this is just for optimization. We can just neglect our visited array. This was just optimization. I have not taken visited array. So then what we are doing? So we have considered 2. We have considered 2. So then what's the next step? Let me erase the visited array just for optimization. Then let me tell you how my code will work. So we have visited this 2. To reach 2, to reach 2, we have to take 8. No matter the path, we are not interested in the path. So then if we want to reach 3, so that's the neighbor. Yes, it's a neighbor. First neighbor is 3. So neighbor is 3. Then path. Path is 8, plus to reach this particular node we have to take 8. So we have to take 16. To reach third, to reach 3 we have to take 16, but the already value present is smaller. So we will not go inside this. So then what we can do? Let's try for this. Neighbor is 1, and neighbor path is 3. Then to reach this particular node we have to take 8. So to reach 1 we have to take 11, but already present value is smaller, so we will just ignore this. Then we can just go to 0. Neighbor is 0. Then path first is 2, this path. Then to reach 8, to reach 8 we have to take 8. To reach 2 we have to take 8. Then to reach 0, to reach 0 we have to take 10 distance, but the value already present is less, so we will not consider this. Then we have this neighbor, so 4. To reach 4, to reach 4 we have to consider 15. So the value is smaller. To reach 4 we have to first take edge, then current weight is 15. So which is smaller? The weight is smaller than already present value. We will just add this in our priority queue. So we have added 4 with weight 15. So then it will just pop out next value. So the next value is this 28, 28. So what we have? Our weight is 8. Then already present value is 8 itself. So you can also write equal to sign greater than or equal to, and it will just work fine. And but in my case I have not added equal to sign, and it will just take more time to process. So first I have added 8 here, then I am processing for 8 again, but there's of no use because I have already considered with the weight present in our answer list. Then next value is also 28. So then we are again processing this. So it's a better to write this symbol greater than or equal to symbol here. Then next value will pop out, which is 4 and 13. So I will add a value here, 4 with 13. 4 with 13. So we have also traversed to this node. So 13. We are not interested in the path. We are not interested in the path. So the path will be, I think, this. Not this. The path will be this. So this is 7. So 7 plus 6 plus 7, 13. Yes, path will be this, but we are not interested in the path. This is just for visualization. So then we will check for neighbors. So I have just got 4. Then to reach 1, so the neighbor is 1, and first edge, then current weight 13. Then we got 22, which is greater then already present value, just ignore this. Then our next neighbor, for next neighbor is this. So neighbor is 2, edge weight 7, current weight 13. So we got 20. Already present value smaller. Then next neighbor is this 0. So to reach 0, edge weight 7, current weight 13. So 20. To reach this way, we have to take 20. So but already present value is 6. So we will just ignore this. Then we again pop out. So to reach 1, we got 14, but already present value is smaller. So that's why this thing improve our time complexity. Then we again pop out a value. To reach 4, we have to take 15. To reach 4, we have to take 15, but already value is smaller. So we will just neglect it. We will just ignore it using the simple if statement. Then we have this array. Our priority queue is empty. Then we just need to return this array. In the function, we don't have to return the array. We have to return a list. So starting from 3, to reach 0, we have to take 6 distance. To reach 1, we have to take 5 distance. To reach 2, we have to take 8 distance. To reach 3 means itself we have to take 0 distance. So that's how this will work. Let me show you the code. So what we got? We have n maximum. So this is like plus infinity, like I have added initially because we have to find a minimum distance. So I have added n times in my answer list. Then we got priority queue. This is similar to Prim's algorithm. So just add your source vertex. To reach the source vertex, we need to take 0 distance. Then we got this priority queue. I've already shown you this code. After that, just return the answer. So let's give it a hit. And now let's talk about time and space complexity. So here we have priority queue, and in the priority queue we are adding each and every each and every edge, each and every edge. We are considering each and every path. So what's the time complexity? So what about time complexity? What we have a while loop and we are adding a particular edge. So we are adding edges. So as you can see, we are adding a neighbor and its weight. So weight is present in the edge, so we are adding edge. So uh, in the priority queue we have log n, but in this case we have edges. Then what we have, we also have this. So number of vertices. So first of all, order of v, then this, but this is not complete. uh, Edges is present here. Then inside the edges we are also accessing the edges. So we are also processing the edges. We also have e. So let me simplify this. What is e? E is an edge between two vertices. So edge, then we need, uh, if we have v minus 1, so we got this. So my so this is the remaining term. So wait. So here we have v minus 1 and v square. What is this? So the minimum edge we have is v minus 1. So in this case we have 2 and we only need 1. We only need one edge. So minimum we can have is this and the maximum we can have is this. In case of dense graph, what is a dense graph? So every single vertex is connected to each and every vertex. So the graph will look like this. So each and every vertex is connected to each and every vertex is connected to each and every vertex. So this is the range. So let's solve this. If we take the log of e will be this. We need to find the worst complexity. So we got this. So then what we got? This is less than equal to, we got 2 log v. So this log e in the worst case can be 2 log v. So just neglect 2. Then we got v plus e log v, yeah. So then also write log v by log v, then e log v, then just simplify the process log v. So we got this, and we got log v. So we will take worst, so we will just take a v in this case. So we got v plus e log v. So here what we have, yeah, v plus e log v. So v plus e log v, that's about the time complexity. What about space complexity? We only have priority queue, and we have our answer. So our answer can be order of v, priority can be order of e. So it will be maximum of order v plus e. So this is our sorry, o is not there, so v plus e. So this is our space complexity. So we have this. So that's enough. So now let's talk about the node. The graph does not work for negative edge. What is a negative edge, and why the extra algorithm will not work? So let's consider it. So let's find out 1, then 2. So 1 is connected to with this with weight minus 1, and we have to find from 2, starting from 2. So what we add? Starting from 2, we will add 0. So we need to find 0. So this is 0 base indexing. 0, then let me change it, 1, 1, 1. So initially we have infinity, and to reach 1 we go to 0. So then we'll pop out, and we will check, is the value greater, present value is greater? Yes. So just change it. Then to reach this node, to reach first, to reach this node, okay, to reach this node we need 0. Then to reach this node we need minus 1 distance. Okay, so just bear with me. So then what we'll add, we will add, to reach 0 we need minus 1. So we only have one edge, so just pop out this. To reach here we need minus 1. So minus 1, the already present value is greater. So then just pop out, just increment, just update the value. Then its neighbor is this. To reach here, to reach here, what we got? To reach 1, we need minus 2 distance. So we have added this. Then we will update. Then we will pop out. To reach 1, we need to update minus 2. So minus 2 here. So first we got 0, then we got minus 2. Then to reach here, then to reach this node, we need minus 3. So as you can see, we are going here, here. So we are stuck in a loop. So that's why it will not work for negative edges. For negative edges, we have Bellman-Ford algorithm. So be sure to check out this video. Bellman-Ford is also very popular and very often used. Then that's enough for today. Thank you all for watching